Okay, let's continue. So now let's give you some introduction to some mathematical tools you need. So we're going to introduce three things. The concept of hazard or failure rates, integration by parts, and the envelope theorem. Okay, the last thing may be new to most of you, so please pay attention to that. Okay, so let's introduce failure or hazard rates first. So consider a bulb whose life is denoted as a random variable capital X. So this capital S means once you light up the bulb, when it will fail. Okay, so you can treat that to be any machine, any computer, whatever. So there is a life, there is an amount of time that it can be used. That's a capital X, and of course it's non-negative. So you don't know what would be the value of X. X is random. So you use small f and capital F to be the CDF, PDF and CDF. So capital F of t is the probability for the bulb to fail by time t. Okay, so that's the probability for the lifetime to be not so long, not longer than t. And then if you ask what's the probability for the bulb to fall or to fail within a certain interval, then you have capital F and t plus epsilon minus capital F of t. Okay, that's the probability to fail in this particular time interval. So we know that small f of t basically means that particular probability when epsilon goes to 0, okay, is the limiting probability. Or you can also say that, okay, it's just the derivative, okay? But as you know, we don't say it is a probability. We say it is a density, okay? Probability density for the bulb to fail at exactly at time t, okay? Given that capital X is continuous, this probability would be 0. Well, what you can say is density. Okay, it's density. Anyway, the failure rate of the bulb, which is defined as h of t, is the likelihood for the bulb to fail exactly at time t, given that the bulb has not failed by time t. Okay, so basically at each time moment, I ask, what's the failure rate? What's the rate for the product, for the bulb, to fail exactly at this moment? Okay, I want to know that. But I don't want to just use f of t because I know the bulb is there. The bulb is good for this particular amount of time. Okay, when I am at time t, I know this bulb has been good from 0 to t. So given this condition, given my information about that, I want to ask what's the probability for x for to be within t plus epsilon, t plus epsilon. Okay, I want to ask what's that failure rate. And then through some very basic derivation, you know this is a conditional probability. So the conditional probability requires you to put this probability for x to be greater than t in the denominator. And the numerator is the joint probability. When you look at that, the second condition is useless, right? Because you are talking about x within t and t plus epsilon. So you're going to get this, and when you take the limit, it's going to be this one. So eventually we can say, okay, the failure rate can be calculated as the ratio between small f of t over 1 minus capital F of t. Okay, so the numerator is the likelihood to be failed, the likelihood to fail at time t, and the denominator is the case that you condition this failure according to the fact that x has been larger than small t. Okay, so it's the concept of conditional probability. So very quickly, let's talk about some examples. If your capital X is uniform between 0 and 1, then your PDF is 1, and your CDF is X, and then your H of X, which is your failure rate, is defined to be 1 over 1 minus X. Okay? When X is 0, this is 1. When X approaches 1, this goes to infinity. You can see that your hazard rate would increase. So basically, that's saying that when this product, when this machine goes on, you expect a higher rate for it to fail when time goes by. Okay, reasonable. A very special case is for your X to be exponentially distributed with parameter lambda. In that case, your PDF is like this, and your CDF is like this. They are just some standard results that you may look it up on Wikipedia or any particular textbook. And then if you plug in small f and capital F into the formula for hazard rate, you're going to see that the hazard rate would just be lambda. And that means if the probability distribution is exponential, then at any moment your failure rate is the same. Okay, if you're talking about some probability random events with this particular property, we typically say that your distribution is memoryless. Okay, memoryless. Anyway, yeah, something about probability. So in general, for any random variable with PDF small f and capital F as the CDF, we define its failure rate as small h, which is f over 1 minus capital F. You don't really need to talk about Bob or a computer or machine or whatever. For any random variable, you can do this definition. Okay, so yeah, it's just definition. For our private type theta, okay, it's also a random variable with f and f. So we're going to impose the following assumption, which is called the increasing failure rate or IFR function assumption. It's saying that I want the failure rate of my theta to be increasing, or say it in another way. If I define capital H of theta to be the ratio of 1 minus f of theta over small f of theta, then I can see this is the reciprocal of the failure rate, right? And then I need my capital H of theta to be weakly decreasing in theta. Okay, so I want my failure rate to increase, or I want my reciprocal of failure rate to decrease. So we are not going to show that to you, but this is true for most of the well-known distributions like uniform. Okay, you see uniform satisfies this. Exponential also satisfies this because all you need is weakly increasing or weakly decreasing. We can show that normal is also following this assumption, gamma, beta, Weibo, whatever. Most of the well-known distributions satisfies this assumption. So it does not really hurt to make this assumption. So in later derivations, we're going to assume that for your private random theta, the failure rate would be increasing. Okay? Okay, the second thing to help you to review or to learn is integration by parts. It's a specific technique to do integration. So suppose u and v are two functions of x defined over an interval a and b. We're going to have the product rule for differentiation, right? The derivative of u and v, the product of u and v, can be found as u v prime plus v u prime, where prime means derivative, okay, first order derivative. So if you have this, then you now can do integration at both sides with respect to x. So this part goes to here, okay, be put as the integrand, and here we also have this part this also goes to the integrand. And then we can do something. First is here. You can see that when we do this integration, you can apply the theorem of calculus or the Leibniz rule, because it's something being differentiated and then taking the integral. So it goes back to itself, and all we need to do is to plug in a and b. Okay, nothing special. And then this is the term that we are really interested in. We put it still at the one side of the equation, and then finally we put the last term to the left hand side. Okay, so that's why its sign would be changed. So this particular formula is what we are going to use as the integration by part formula. When you have one integral to do, then you separate it into two parts. Okay, into two parts, and then following this formula to carry it over. Okay, for most of the time, we would like to use some abbreviated formula to help us memorize it. Okay, and the way we say it is that u dv equals uv minus v du. Okay, u dv equals uv minus v du. So let's see some examples. Suppose I want to calculate this. I want to calculate the integral of x e to the power of x from 0 to 1. So I don't have any way to do it directly, but I can separate this thing into two parts. I can say u is x and dv is ex dx. And once we do that, then according to our formula, let me write down it again, u dv equals uv minus v du. Then we can know here we should have uv, and then we're going to plug in the upper bound and lower bound to it. And then we also have minus v du. So here, of course, u is x, so u is x, nothing difficult. And if u is x, then when you take a first order derivative of that, that's going to be just 1. Okay, so you're going to have du equals dx. Also, if your dv is this guy, then you need to be able to find v. Okay, and you know v would be e of x, e to the power of x, because the derivative of e to the power of x would just be e to the power of x. Okay, that's how you find v according to dv. So once you do that, then the first part can be calculated. You plug in 0, you get 0. You plug in 1, you get e. And the second part can also be done because you know how to do this integration. This integration simply gives you e to the power of x from 0 to 1. So you again plug in and you get e minus 1. Eventually you get 1 as the outcome. Let's use another example to do a further illustration. Here we are actually talking about 0 and 1. Sorry. So when I want to do this, I don't know how to do it, but I can use integration by parts again. So I let u to be x squared, dv to be e to the power of x dx. And then I have this. This is uv. Okay, uv, the same thing. And here I have v du. Here, du would be 2x times dx instead of just dx, because x squared, if you differentiate it, you get 2x. So now again, here I can get e, nothing special. And here, this is something that I need to do integration by part again. If I take 2 outside, then I get something like this. Okay? Not easy, but I know how to do it because this is exactly what I did just a few minutes ago. So I can carry on and eventually find this as my final outcome. Okay, so that's integration by parts. Both of the things will be used later when we do the solution. We will try to find the solution of our optimal contract design problem. So you're going to see them later. Thank you.